okay to go over it again. I mean, the plan was to go over it again so that because it's an important concept, you know, so it's okay to go over it again, but you don't have to spend too much time if you're concerned about time. Yeah.
Okay. So essentially, so basically, we know, at least by now in this class, we all know what our target population is, right? We know what our study population or what our sample population is. And we know that the estimate we're going to be getting, because we're collecting information from just our sample, the estimate we're going to be getting is going to be a sample estimate, which is what we call a statistic. Whereas what we are actually interested in is not the distribution of physicians in these 80 people we selected. No, we're actually interested in the distribution of physicians in the entirety of the class, which is the population. And that is what we call a population parameter. So the equivalent of the parameter in the population is a statistic in the sample. So the question that we answer when we talk about inference is actually, how can we move from our statistic to actually know something about our population parameter? How can we move from the statistic in the population and make accurate applications in the parameter in the target population? And one of the reasons why that is really possible is from the work of some very smart statisticians and mathematicians who are able to, from a lot of thinking and a lot of experimental validation, are able to show what we call the central limit theorem, which is that, you see, if we have a class of 800 people, if I select 80 people from them, some people might end up being in the sample. If I select those 80 people today, if I roll my dice and I selected people, Temi might end up being in the sample, Labra might end up being in the sample. If I select another sample tomorrow, if I wanted to redo it tomorrow, and I select 80 people again, the three of them might not be in the sample at all. If I do that again, the people who were in the last sample, a large chunk of them might not be in this sample again. So someone would ask, so how do we know that what we get from this sample tells us something about the population? It turns out that if you draw many samples like that, and if you take the statistic in that sample, say, for instance, what we're looking at is the distribution of physicians. If we take a sample of 80, 80, 80, 80, and we take it multiple times, and we look at the distribution of physicians, some people have actually done that experiment and see that as long as you're randomly doing it, the number you get, when you plug all those numbers together, it gives a normal distribution. So if you take this sample repeatedly, there is a connection. The statistic that you estimate from this sample does not just go up and down. It's just not random. No, it's just not, irregular. No, that statistics follows a particular pattern. And what they've been able to show is that statistic follows a uniform distribution. And that uniform distribution, the population parameter kind of coincides with the middle point of that uniform distribution. Let's hear this very well. If I took the 80 people on Monday, I found how many physicians are there. If I took another 80 people on Tuesday, we assume that I'm randomly selecting them. I take another 80 people on Wednesday. I take another 80 people on Thursday. Now, say there are actually 500 physicians. There are actually 520 physicians in the class. What you would find out is that out of the people you take, you don't just get random swings. You get something around 50, 52, 54, 50. You get to that. So even though all those numbers will not be the same, some will be further away, some will be closer. But when you look at all those numbers again, all those numbers together, they will form a normal distribution. And a normal distribution is important for certain reasons. I don't know if you've done that in the last class, because there's something we know about normal distributions. We precisely know when you have a normal distribution, we know what the mean is, and we know the chances that particular numbers will fall within a certain range from the center of that distribution. And because we now know that when you take samples and you plot the statistic from that sample, it gives a normal distribution. And the center of that normal distribution that you get from the samples actually coincides or approximates the actual population parameter, the actual figure you would have gotten if you had collected information from the whole target population. Therefore, we are able to think about, a relationship between the population parameter and the statistic we get from our sample. So this might not be very clear right now, but all we should know is that when you try sample, that what you get from that sample, it's not just, there is some variation. It's different from what you would have gotten from the population. It's different from what you would get from if you selected the sample a second time, or you selected it, or what would you get? You would have gotten if you selected it on another occasion. But there is some relationship, and based on what we know about the theory of the normal distribution, we can have a sense of where should the statistic we get from our sample lie in relation to what we would have gotten if we have gotten information from the whole population. And that essentially is the core of what we know as the central limit theorem. So now we would go to hypothesis testing, because here is what would happen. So if you get a sample right now, when you get a sample from your population, remember that there is some element of chance in the selection of your sample, meaning that when you roll your dice, you get 80 people today. If you roll your dice tomorrow, the 80 people you will get are going to be different from the 80 people you get today. We just know that everybody has a chance of getting in, but not everybody would get in. So there is some chance, but how do we take care of that chance? How do we account for that chance so that when we're thinking about this statistic and we're drawing inferences from it, we know that there's an element of chance and variability around it. We'll talk about that down the line. But just in terms of procedure, just in terms of procedure, when we get our statistics from this sample, from the 80 people, we still have other things to do to ask the question. Because we know that the statistic we get from here is not exactly what we would have taken from the actual population, there are still other procedures that we need to follow to account for this chance. And that we do in the context of hypothesis testing. So I'm just going to be talking about the mechanisms of hypothesis testing right now. The first thing we do in hypothesis is that we determine what our null is. And the null is basically, what should not be true for the question we are trying to figure out to be accurate. So for instance now, say what we're suspecting is that there are too many physicians in this class. So that's why we're collecting this information to know, are there actually more physicians in this class than we want? The null hypothesis here would be that there are too few physicians in this class. But there are several ways of expressing that. We might say the number of physicians minus the number of non-physicians in this class is equal to 0, which is the same thing as there are not, physicians and non-physicians are the same in this class. We don't have too many physicians. We don't have more physicians in this class than non-physicians. We might say the number of physicians in this class is equal to the number of non-physicians in this class. And that's a null hypothesis. When you look at the slide, you can see how you can see the symbol that we use for the null hypothesis. Now, the essence of a statistical analysis is really to test whether the figure you get, supports the statistic you get from your sample is in consonance with this null hypothesis. In which case, we say that we cannot reject the null hypothesis. But when you do your analysis and you see that the figure is not consistent with this null hypothesis, in that case, we can say, well, we can reject the null hypothesis that physicians are equal to non-physicians, meaning that, well, not exactly, but the way we interpret it practically is that now it looks like we have more physicians in this class than non-physicians. So the steps to follow in hypothesis testing are the 6 steps you see here. We have to state what our null hypothesis is and the alternative hypothesis, which is really what we're trying to find out. Now, you have to understand that the sample, the statistic that we're going to get from our sample, we know is not exactly what you would get. It's very unlikely to be exactly what you would get if you had studied the whole population. But there are statisticians that have figured out a number of ways for us to know how close, how much of confidence do we have that this is actually, close enough. This is pretty close to what we would have gotten from the population parameter. But that comes at a cost. And the cost is that we often cannot have 100% confidence that this is what we would get from the target population. But we can estimate how much of confidence we would have. Essentially, we can assume, we can specify. So, like I said, for instance, look at the examples I gave you earlier in the class experiment that we had earlier. You might be interested in knowing exactly how many people are in this class. In that case, you can't work with the sample. Or you might just be interested in something like, well, are physicians generally more in this class? And you might be comfortable, you might be fine with saying, well, even if I'm 80% sure that physicians are not the majority in this class, that's enough for the kind of decision I want to make. So because we cannot be 100% sure, we have to decide at what level are we sure, at what level are we comfortable with being wrong. And traditionally, many people would say, if I'm 95% certain that this number is useful, this statistic is useful, that's good enough. So how much of chance we are willing to take on being wrong, on believing, on being wrong, on believing our finding when in fact it was wrong, is what we call the alpha level. So that's the chance that the null hypothesis was actually right when you are actually failing to reject it. So after you have specified, you have determined what alpha level you are comfortable with. Usually most people would say 5%. If the chance that I'm wrong is more than 5%, maybe this is not useful enough. Then we go ahead and compute the actual statistic we're looking for. That statistic might be the mean, it might be the percentage of physicians, it might be the median, there's a number of statistics. It's just a statistic that represents what we're actually interested in knowing from the population. And after you have computed that statistic, based on your statistic, based on your alpha level, you can determine what we call a p-value. So the p-value, we would come to the mechanics of determining, the p-value is related to the p-value essentially. So the p-value essentially is what you have, is the actual probability that you now compute. The actual probability that with the number, with the statistic you have estimated. So here's what happens. For instance, I'm trying to figure out whether there are more physicians are more than 50% in this class. My null hypothesis is that physicians are 50%, those who are not physicians are 50%. And I'm saying that, well, if the chance that I'm wrong is not more than 5%, my alpha is 5%, I will be fine with this data. Now, when I compute look at my sample and I compute and I figure out that, yeah, well, from this sample, it looks like 80% of people who are physicians in this sample. I need to determine something called the p-value, which is, what is the likelihood that, given that I've seen 80% in this sample, what is the likelihood that when I look at the population itself, physicians are actually fewer than 50%? For instance, if I look at the sample, for instance, say my sample, I got 50, I find out that 51% of my sample are actually physicians. You might say, well, 51%, we know that this is not an exact number. So maybe 51% is too close. We might not, we don't, 51% is just too close to 50% that's actually the cutoff for in our hypothesis. So I'm just not confident enough to make a decision about whether, if I look at the general population, doctors or physicians would have been more than non-physicians. But if you selected 80 people randomly, and all the 80 people turned out to be physicians, the chance that you are wrong, that if you have selected the whole population, physicians would have been fewer, the chances are almost non-existent. So the p-value essentially is that given the figure that I've now gotten from my sample, what is the chance that I'm still wrong? So a lot of times when people, arbitrarily, some people say if the chance is that there's less than 5% chance that I will still be wrong, then I'm happy to just live with the conclusion that there are more physicians in this class. And that's why many people would use a p-value of 0.05, which is saying that 5% that you're wrong, given the figure that you have right now. So many people use that as cutoff. If I calculate the p-value based on the statistic that I've gotten from my sample, if the p-value tells me that there's less than 5% chance that I am wrong, then I would live with the fact that it looks like my hypothesis holds. My alternative hypothesis holds. So after you have computed the statistic, often you will figure out what your p-value is. But I also want you to know that that 5% p-value, even though it's a convention, it's a convention. It's because many people feel comfortable at that level and they use it. There are decisions that you might want to take where you don't need to be that precise and confident, where you're like, well, if there's even a 70% chance that I'm correct, that's fine. So my p-value doesn't have to be 0.05. It can be 0.3. But for the purpose of a lot of the papers that we see in the literature that we read, and for most of the work that we do, the convention that people follow is 0.05, and that's good enough in so many situations. But what you should just not, but now, because when you're reporting your statistic in your paper, the level of doubt that you are comfortable with is not necessarily the level of doubt that all your readers are comfortable with. Therefore, don't just go and say, my p-value that I computed here is less than 0.05. It is always good to write your actual p-value so that the reader can make their own determination about whether the p-value that about whether the data, the statistic that you have estimated is good enough for them, and they're willing to live with the likelihood of being wrong that your statistic represents from your computation. So I'm just going to move on from this slide at this point. But in terms of hypothesis testing,
sorry. Before you go, can you go over the difference between the p-value, the alpha, and the level of significance again? It looks like that's a funny point for people.
So alpha is just essentially a synonym for the level of significance. Now, what is that level of significance? What we are saying is level of significance. When we say level of significance, what we actually mean is that a level that you have specified that, if the chances that I'm wrong is not beyond this level, then it is good enough for the purpose of this study. So if the chances that, so for instance, we're just interested in whether there are more physicians in this class or not. From all the work we've done, if the chances that we're wrong about that decision is not more than 5%, then that's fine, we're good to go. That's what its level of significance means. That's what your alpha is. So your alpha in that situation is 5%, 0.05. Somebody might say, well, even if the chances that we are wrong is up to 30%, that's fine. I mean, this is not a question of life and death. We just want to buy. I mean, we're just making this computation to know whether to buy more snacks or not. So we can keep our alpha at 0.3. So that's a level you specify about before you do your computation about, well, if the chances that I'm wrong doesn't go beyond this level, then I would take the, I mean, I would take my alternative hypothesis. Now, given what you actually, the number you actually get from your sample, after you have collected your data from your sample, the p-value is the chance that you now actually compute given the number you get. For instance, you select the 80 people you get, and you find out that out of the 80 people, all the 80 people are physicians. Your p-value would almost be 0, because the chance that you would be wrong, and there will be more physicians in the actual population, and just this sample has all 80 of them are physicians, the chances are almost non-existent. But if you get something like 51 people, like 41 out of the 80 people being physicians and 39 being non-physicians, you might not be very certain. When you compute your p-value, there's a way we compute p-value. That's just the scope of what I'm going to be discussing here. But your stator will give you a p-value for the figure 41 that you get. That p-value, most likely, that p-value would be much higher, meaning that the chances that you are making an error and physicians are not more in the actual population are much higher. Because when you get 4139, it could go either, it could be either way where you actually collect information from the whole population. So the p-value actually reflects the chances that you are wrong based on the actual statistic that you have gotten from your sample. Now, when you get the actual p-value, you now compare it with the level you have specified earlier. So now say you get a p-value that is 0.00001, and you have said that earlier that my alpha is 0.05, meaning that my p-value is less than 0.05. If the chance that I'm wrong is less than 0.05, then I would agree, I would believe that there are more physicians in this class, and I would buy more snacks. So when you conduct your study, you find 79 physicians out of the 80 people, your p-value becomes 0.00001. You say, yes, the chances that I'm wrong is actually less than 0.05. Yes, for the purpose of this study, we would conclude that there are more physicians in this class. But say you collect your information from the sample and you find that 41 are physicians, 39 are non-physicians. Your p-value is likely to be much, much higher. Maybe now you get a p-value of 0.03. At 0.3, I say, well, 0.3 is bigger than 0.05. The chances that we are wrong is about 30%. That's too much of a chance, maybe. So, of course, this is a simplification. There's a number of other parameters that goes into the computation that links the p-value to the number, to the statistic you get from your sample. But for the purpose of for the purpose of just understanding what we're talking about here, just know that the p-value is actually linked to the statistic you actually estimate from your sample, and then you would compare that p-value to what you have specified as the level of risk you are willing to take, which is the alpha, which is the level of significance. So once your p-value crosses that level, meaning that the actual computed level of risk of being wrong exceeds what you have specified as the level of risk of being wrong that you can tolerate, and at that point, you cannot reject your null hypothesis. Does that bring some clarity to? Okay. And we would have more opportunity to still talk about this as the course proceeds. So I think a lot of what we talk about here is just the p-value is the probability that you are wrong given the actual value that you've now gotten from your sample. Because even though you have done everything right, even though you randomly selected your sample, chance by chance, you might end up today selecting people that are a little bit skewed away from the population. And when you select those kind of people, by chance, you might just have 41 people who are physicians out of the 80, when in fact, in the population, there are actually just like 398 physicians. Meaning that, so essentially, a lot of this slide is just a lot of what we have discussed about the p-value and alpha. And like we said earlier, p-values are not hard and fast. The convention a lot of times is that we use 0.05, but a lot of times it depends on the reader, it depends on the decision you want to take and how much of risk of being wrong that you would be able to tolerate.
I have a question here. So if the p-value is higher than alpha, so say you have a p-value of 0.16 and your alpha is 0.05, do you reject the null hypothesis or do you fail to reject it?
You fail to reject the null hypothesis.
Okay. So what does that really mean in this
So
case?
say your null hypothesis, remember that your null hypothesis is the opposite of what you're trying to find out. Say your null hypothesis here is that physicians are equal to non-physicians in this class. They are 50-50. Now, when you get your statistic, you find the number of physicians who are in this your sample, you compute the p-value, and then you get 0.24. And your alpha was 0.05. You have said that once it's more than 0.05, and now you get 0.24. When you get 0.24, that's more than 0.05. So you fail to reject your null hypothesis. You fail to reject your null hypothesis. And what that means is that, well, I cannot say that there are more physicians in this class. My null hypothesis is what I will still stick to, which is that there's no difference between physicians and non-physicians in this class.
Yeah, I just wanted to also say, sorry, that the language is a little clunky, right? Like it's not so straightforward, but that is the convention. So if you reject the null hypothesis, so you have two negatives. You have a null hypothesis, which is negative, and then you have to reject it. That means that you then have a positive, which means that your relationship is significant, right? But if you fail to reject the null, so you now have three negatives. It's a little clunky, but that is the convention. The reason why it's the convention is because we are working in the probability space. Nothing is really sure. So we are really saying what the chance that I am wrong, is so small, like Dr. Mota explained. So because the chance I'm wrong is so small, that's why I am rejecting the null. But if the chance I am wrong is high, where your p-value is more than 0.05, then you will say that you fail to reject the null hypothesis. Clunky, but it's chosen to be like that because of the way that the math is set up in the background.
And sometimes I've seen people ask me, why can't I just say, so now I've just accepted the alternative hypothesis. So, in practical terms, that is what you do. But there's a reason why that language is not framed that way. And that's based on, the fact that we're working in the space of probability theory, like Kabir just mentioned. But in practical terms, that is what you're practically doing. You're sort of just accepting your alternative hypothesis now when your p-value is lower than your alpha.